Hey, everybody, it's Doug Green, and I'm the publisher of Technology Reseller News. And I'm very pleased to have with us JB Baker, who's the Vice President of Products at ScaleFlux. JB, thank you for joining us today.
Thank you for having me.
Well, we're going to be talking about not just AI, but one of the impacts of AI, and then we're going to discuss how possibly to mitigate it. And the big story here is energy. The big story is AI uses a lot of power.
Yeah. I mean, I don't know if how many of your audience has watched the NVIDIA GTC keynote, but the discussion there about just the power per processor, it's going through the roof. Now, granted, they're dramatically increasing the efficiency. That is, how many flops or how much work they can get done per CPU core or GPU core, but it's still that each generation is consuming significantly more power than the prior generation, and there's several problems that come out of that.
So what's driving that? What's happening?
Well, recently in the industry, of course, there was the OpenAI with ChatGPT coming on the scene, and just everybody kind of getting this, hey, AI is here and it's real. And we can use it for a lot of things. And it's not just LLMs, but it's the digital twins and things that NVIDIA talks about to run simulations and improve manufacturing efficiency. So it's just a core shift in the thinking about how we use our compute infrastructure and driving dramatically heavier use of the processors and GPUs, which then are going to pull on. We need more memory. We need faster memory. We need faster networking to deliver data to the memory, to deliver it to the GPUs. We need bigger, more storage to handle all of the data that we want to work with to run these models. So it's just a kind of a self-reinforcing cycle there.
Now, what are the primary obstacles hindering the implementation of more sustainable IT infrastructure to support AI and also machine learning?
Yeah, it's there's a bunch of things there. We've got, in deploying the new technologies, anytime you want to change something to make it, to take advantage of a more efficient technology, there's that resistance to change. Either the fear that it's not going to work right, or just the lack of knowledge in how to use it. There's also the resources to do any kind of implementation or integration work that might be required to leverage the new technologies. For example, if you have to rewrite your software application as an enterprise user, but you don't own the code, how are you going to get that done? You're putting it back on that application vendor to rewrite the code to take advantage of new technologies. And so there can be a mismatch there. And then what we've experienced also is that there can be a mismatch even within the company. So you have a large scale enterprise and they have all of these initiatives around improving efficiency and power or deploying AI. But you've got the software guys have one set of indicators that they're working to or goals. You have the hardware guys that have a different set of goals. And then you got the IT budget and procurement guys that have a different set of goals. And unless you can get all of them working together on a common deployment, then it can be a real challenge there, just those organizational challenges.
What about solutions such as SSDs?
So SSDs in general are very, they're pretty ubiquitous at this point. There's not a lot of differentiation across and I focus on NVMe SSDs, which are the higher performing class of enterprise NVMe or enterprise SSDs, the newer interface, newer protocol. And over the past decade, as these have become ubiquitous, there's differentiation has shrunk across vendors. And you've got server vendors and system integrators that really like that there's not a ton of differentiation, because they can then substitute any drive they want at any time. So bringing in innovation into the SSD world is a challenge, because you bring in something where, hey, this SSD stands above the rest of the pack significantly, say twice as fast, or offers 2 or 3 times the endurance, can reduce latency, can expand its effective capacity, and offer you more effective terabytes per dollar. And it's a challenge to get that through the supply chain.
So, what specific benefits do SSDs with computational storage and ARM-based computing offer in terms of energy savings and performance compared to traditional storage systems?
Yeah, there's several benefits here. With computational storage drives, what we're doing is moving compute tasks that would have ordinarily been done in a general purpose core in the CPU or the GPU, and we're pushing those down into the drive. And by doing that, they can be done with specialized processors or even hardware engines that can perform those tasks orders of magnitude more efficiently. In the ScaleFlux drives, for example, we're doing data write reduction technology, which is data compression. And we can do that in a hardware engine, and we can do in 1 watt what it would take hundreds of watts of x86 cores to do. And so to achieve the same level of throughput that we can achieve in that compression decompression function, it would take hundreds of watts and tens of x86 cores to perform that same function. So just massive efficiency improvement. And then the other byproduct there is that contrary to ordinary use of write reduction technologies and compression, by doing it in the drive, we reduce how much data has to be physically written to the NAND, which improves the performance and the latency of the drives, which is like just kind of mind-blowing for people that compression is now an accelerator. But that is the case, is that we're able to write less data and keep the NAND less busy to do the same amount of work.
Okay, and so in what ways does the implementation of ARM-based computing in ScaleFlux's technology contribute to reducing latency and improving energy efficiency in AI applications?
Sure. By using ARM technology, ARM is very well balanced in terms of the performance and power, and they have a variety of cores that can be integrated into application-specific integrated circuits or system-on-chip controllers, SoCs. And that's what we do in our controller that we've developed for the SSD, is we integrate ARM cores for to right-size the performance and power for that envelope of an SSD. And then we also add in hardware compute engines to accelerate functions in the drive. Doing those things not only translates into a more efficient drive, which is great, but it also translates to efficiencies at the system level. So as an example, what we'll show here is just writing data to the drive. So we said, hey, we're going to use RocksDB, which is commonly used as the background for analytics, and we're going to transfer 20 gigabytes of data to the drive. And instead of asking the host CPU to do LZ4 compression, a lightweight compressor, we're gonna turn that off and let the drive handle the compression. So if I can get it to run. Okay, there we go. So in the right-hand side, what we're showing is the cumulative power, watt seconds, that was consumed to complete the task, as well as how long it's taking to complete. So with the CSD, what we see is that the instantaneous power is not any different. So the overall system is running at the same level, but the job completes significantly faster. So it takes 1.7 times the amount of time for the job to complete with using the CPU to do the compression versus offloading that function to the drive. So now you're saying, I'm going to take 70% more of my server time. I'm going to take 70% more power to complete the same work with an ordinary drive versus using the advanced computational storage drives.
So you're actually using less energy, but it's faster?
Yeah, it's both faster and less total power. So like on an instantaneous basis, the server is still running the same amount of total power. It's because our drive is running the same watts as the other NVMe SSD, and the processor is consuming the same power, and the fans and the memory, but you're finishing the job faster, so your total watts consumed is significantly lower.
So where and when can this be applied?
Really anywhere. We've had these drives shipping for since 2022. The next generation we'll be announcing here. We'll be shipping it later this year. We have dozens of customers who have deployed this already for various applications, database applications, software-defined storage, high-frequency trading, cloud-based applications, managed service providers and cloud service providers globally utilizing our drives to improve their efficiency.
And JB, I think you actually have a case study that sort of dramatically demonstrates like the type of savings that can be had.
Yeah, so this was our lab testing, but what really matters is what customers see in the real world. So we have a major cloud customer that they run a hybrid transactional analytical processing database. It's a mouthful. And they do it in clusters of 30 petabytes. What they had with ordinary drives was, which you see there in the gray in the baseline, is it took them 650 servers, 7,800 SSDs to provide this 30 petabytes of storage. They have replication and things in there, so there's more physical than the 30 petabytes we talk about. But then they deployed ScaleFlux drives with that built-in write reduction technology and expanded the capacity of the drives. And what they found was they could deliver the same 30 petabytes of storage, the same throughput in terms of transactions and queries completed, the same levels of latency with 60% less hardware. So, that's a less cost up front, right? Less power in operations, less data center floor space, less cooling. And then probably the biggest thing that they love the most was it's fewer things to fail. Because what I hear from customers a lot as we talk about what's the biggest problem with their infrastructure, it's if we're talking to the hardware teams, and it's or the operations teams, it's I don't like those calls when I'm not at work that say something broke,
right?
And I have to fix it. So if you can eliminate those, you make my life better.
So are there other technologies coming down the pike to help with efficiency and scaling for AI?
Yeah, absolutely. Not only do the GPU vendors continue to innovate within their processors to make them more efficient in terms of work per watt, but there are additional technologies that are centered on near data compute. So not just pushing it to the drives, but pushing it towards the memory. And then also there's the CXL technology, which is going to expand the available bandwidth and capacity of DRAM. So we'll throw the teaser out for your people of the memory wall as a problem for scaling AI performance, and that is just having enough capacity and enough bandwidth in the DRAM to feed that processing beast.
Well, JB, I really want to thank you for talking to us again today. Sustainability is huge. Everyone's talking about it, but we actually just saw a first-class demonstration of how possibly to tackle it, and just how important, how big a deal this could be especially on your balance sheet and a lot of other places, even struggling to just come up with the power to do it. Where can we learn more about ScaleFlux?
Well, we're scaleflux.com, so we should be pretty easy to find us. And then we're on LinkedIn as well with just search for ScaleFlux and we'll pop up there.
Well, JB, again, thank you very much. I hope we get to do this again soon. Very timely. Thanks again for your time.
All right. Thanks, Doug.